Dear student, in our last video we learned statement for Gauss law or Gauss theorem. We learn how to apply the Gauss theorem for application part, and again in case of study the application part of Gauss theorem, I already explained in last video. First you have to assume on Gaussian surface. In that Gaussian surface you have to calculate the total electric flux, then you have to apply the Gauss theorem. These are the three important steps we learn. By using these three important steps, next important part is application of Gauss theorem in electrostatics. In that application, first important thing is expression for electric field or intensity at a point due to infinitely long straight uniformly charged wire or conductor. I repeat, expression for electric field or intensity at a point due to infinitely long straight uniformly charged wire or conductor. And again the diagram is like this. We consider one infinitely long uniformly charged wire. This is the uniformly charged wire. Over this wire positive charge is located. Total strength of the charge is Q. Total strength of the charge is Q. Now this wire or conductor we call it as a rod. Over this rod on this surface the distribution of charge Q is uniform, and again this one is a wire or conductor, or we say that rod. Automatically distribution or continuous charge distribution is mainly giving idea related to linear charge density. The linear charge density we denoted by letter lambda, where lambda is nothing but total charge on this surface per unit length. Now it is called as a lambda, and again we consider one uniformly charged wire or conductor, and again to study the application part of Gauss theorem, around this conductor we consider Gaussian surface, is also called cylindrical surface. I already told there are three important steps to study the application of Gauss theorem. First you have to assume on Gaussian surface. This Gaussian surface is just imaginary. I consider one imaginary cylindrical surface. That imaginary cylindrical surface is called Gaussian surface. Again, consider straight conductor or infinite length of uniform linear charge density sigma. I already told linear charge density on that rod or wire is a lambda. Let P be the point at a distance r from the conductor. See the diagram. In a Gaussian surface or cylindrical surface, I assume the point P. That point P is at a distance is equal to r from the wire or conductor. At a point P, electric field E is acting. I consider small surface area at a point P. That surface area is delta S. That surface area is very small. That's why it behaving like a vector, is acting normally outward. This arrow mark indicates small surface area delta S. In this diagram, at a point P of surface area delta S, electric field and surface area vector or area vector both are in the same direction. Angle between E and delta S theta is equal to 0. And again there are two important surfaces we taken. One is curved surface by using this cylindrical surface. Another one is end face of the cylinder. There are two end face of the cylinder in case of this diagram. Now to calculate total electric flux is the second step. I already assume the Gaussian surface or cylindrical surface is the first steps to study the application part of Gauss theorem. Second step, we have to calculate the total electric flux in that surface. The total electric flux in that surface pi is divided into two part here. One is pi 1 and the one is pi 2. It is a flux is get added, because I already told in a last video electric flux is a scalar quantity, is a scalar addition. I assume that equation number 1, where pi 1 is the electric flux through the end face of the Gaussian cylinder or Gaussian cylindrical surface. Here pi 1 is the electric flux through the end face of the Gaussian cylindrical surface. This one is an end face. Again in case of this end face, you already know about that. This area part is acting normally outward like this. And again here on this surface electric field is acting outward like this. angle between electric field and area is 90 degree. Theta is equal to 90 degree. You already know the expression for flux. Flux is equal to E into delta S into cos theta. Here angle between delta S is nothing but area and electric field is theta is equal to 90 degree. That's why this flux becomes 0. That's why pi 1 electric flux through the end face of the Gaussian cylindrical surface is equal to 0. And second important thing is pi 2 electric flux through the curved surface. Here these two are the curved surface. In case of curved surface, there are two curved surface are there. Automatically we have to think about entire cylinder. The surface is like this. Automatically the total electric flux is summation E into delta S into cos theta, and that becomes pi 2 is equal to summation E into delta S, where we assume theta is equal to 0. As I already told, in a curved surface, angle between E and delta S is theta is equal to 0. Automatically that equation becomes cos 0 is equal to 1. Equation becomes pi 2 is equal to summation E into delta S. But around the curved surface, each and every point, electric field is uniform because distribution of charge is uniform. That's why E is the same throughout the surface. That's why E is taken out. The remaining is E into summation delta S. Therefore, equation 1 becomes that equation 1 involves the two flux, pi 1 and pi 2. Pi 1 is for end face of the cylinder and pi 2 is for curved surface. Here pi is equal to end face, total flux is equal to 0 because theta is equal to 90 degree, and for curved surface flux is E into summation delta S. Therefore total electric flux in case of Gaussian surface is equal to E into summation delta S. We assume that equation number 2, where summation delta S is nothing but total area of cylindrical surface, because in a cylindrical surface, if I consider summation delta S is a small surface area, all the summation delta S joined together for a curved surface, I will get a total area of a cylindrical surface. Entire total area of a cylindrical surface like this. Therefore, summation delta S is equal to total area of cylindrical surface is equal to 2 pi RL is a surface area of a cylindrical surface. From equation 2 we get pi is equal to E. In place of summation delta S we have to take 2 pi RL, that I assume that equation number 3. Now according to application part of Gauss theorem, first I assume the Gaussian surface. In that Gaussian surface I calculated the total electric flux, that we call it as equation number 3. Then the third step is you have to apply the Gauss theorem to get the expression for electric field. According to Gauss theorem, total electric flux pi is equal to 1 by epsilon naught into Q. Equation number 4. When I want to compare equation 3 and 4, both are equal to total electric flux enclosed in the Gaussian surface. From equation 3 and 4 we got E into 2 pi RL is equal to 1 divided by epsilon naught into Q. On rearranging the equation we got E is equal to Q divided by 2 pi epsilon naught into R into L, where Q divided by L is called linear charge density denoted by letter lambda. Therefore equation becomes E is equal to lambda divided by 2 pi epsilon naught into R. Here L is the length of the cylindrical surface. You have to take it like this. L is the length of cylindrical surface. Now by using this equation, Q divided by L is equal to lambda, linear charge density, at the end we got E is equal to lambda divided by 2 pi epsilon naught into R, where lambda indicates linear charge density. In a given wire or rod or conductor, linear charge density is more, electric field is also increases. Automatically lambda is positive, that indicates that electric field is acting outward, positive surface. If lambda is negative, automatically electric field is acting inward, that surface got a negative charge. Here E is the expression for electric field by using a uniform wire or rod or conductor. E is equal to lambda divided by 2 pi epsilon naught into R, and this one is one of the important part for exam, mainly for 5 marks, and is the diagram and it carries 1 marks. These are the explanation related to get the expression for electric field or intensity at a point due to uniformly charged straight wire or conductor. This is the diagram representation. At the end we got the expression for electric field. E is equal to lambda divided by 2 pi epsilon naught into R. Now, continuation of this concept, next important application part, we call it a second application part of Gauss theorem, is nothing but expression for electric field or intensity due to uniformly charged infinite plane sheet or plane surface. And again, in case of this, we consider infinitely thin plane sheet like this, and consider an infinitely thin plane sheet of positive charge. We indicate Q is the positive charge distributed uniformly on this plane sheet, and surface charge density of plane sheet is sigma. The diagram is like this. We consider uniformly charged, positively charged plane sheet, and thickness is negligibly small, that's why we call it a thin plane sheet, and distribution of charge is uniform on the surface. Automatically we leading towards the concept called surface charge density. It is denoted as sigma is equal to Q divided by A or Q divided by delta S, and again Q represent the total charge, A represent the area or surface area. Again, to study the application part of Gauss theorem for infinitely plane sheet with uniform distribution of positive charge, first you have to assume the Gaussian surface. Again, in case of this diagram, this cylinder represent the Gaussian surface. Again, this cylinder represent the Gaussian surface. First you have to assume the Gaussian surface is a step number 1. In a step number 1, we consider Gaussian surface. The cylinder represent the Gaussian surface. In a cylinder, we consider 2 ends. One end is P of surface area A, another end is Q of surface area, again it is A. In both the side, electric field is acting outward. It should be like if you take one notebook or any one surface where electric field acting outward like this, electric field acting outward like this in this surface, and here we consider cylinder as a Gaussian surface. Second important step is to get the application of Gauss theorem in electrostatic. I assume the Gaussian surface. Second step is you have to find out the total electric flux in that Gaussian surface. Therefore, total electric flux pi is divided into 3 parts here. It is equal to flux for a curved surface, flux through a point P, flux through a point Q. Here flux is a scalar quantity, that's why it is a scalar addition. Here flux is equal to flux through a curved surface plus flux through a point P and flux through a point Q. I already told in a Gaussian surface we consider 2 ends of a cylinder. One surface is Q and the surface is P with the surface area A each. Electric field is uniform, distance is also same, that's why total flux is considered by 3 parts here. One is flux through a curved surface plus flux through a point P plus flux through a point Q. I assume that equation number 1. We will discuss all these 3 flux one by one, where flux through a curved surface is equal to 0. Here this one is the curved surface. In a curved surface, area vector is acting normally outward, electric field is acting outward from the surface like this. Angle between area vector and electric field is theta is equal to 90 degree. If theta is equal to 90 degree, we already know about that. Electric flux is equal to E delta S into cos theta or E into A into cos theta. Theta is equal to 90 degree, that flux becomes 0. That's why in both the side, over the curved surface, electric flux is equal to 0 is the first thing. Second point, flux through a point P and flux through a point Q. Here flux through a point P and flux through a point Q, in both the case, angle between area vector and electric field, theta is equal to 0 degree. Here is also theta is equal to 0 degree, because area vector and electric field both are acting in the same path or same line. Automatically angle between E and area vector is equal to 0 in both the end P and Q. By using this, flux through a point P is equal to EA cos theta, actual equation where theta is equal to 0, we got E into A. Similarly, flux through a point Q is equal to EA cos theta, where theta is equal to 0, we got E flux is equal to E into A. By using these three expressions, equation 1 becomes, where equation 1 divided into three parts: flux through a curved surface, flux through a point P, flux through a point Q. Automatic equation 1 becomes flux is equal to, flux through a curved surface is 0, flux through a point P is EA, flux through a point Q is EA. It becomes EA plus EA. Automatically flux is equal to 2 into EA. We assume that equation number 2. Now we got the expression for flux enclosed in a Gaussian surface. After second step, calculating total flux, we have to apply the Gauss theorem is the third step. According to Gauss theorem, you already know about the total electric flux enclosed in a Gaussian surface is equal to 1 by epsilon naught times net charge, that is Q. I assume that is equation number 3. When you want to consider equation 2 and 3, both are equal to total electric flux enclosed in a surface. By comparing, we got 2EA is equal to 1 by epsilon naught times Q. That becomes E is equal to 1 divided by 2 epsilon naught into Q divided by A, where Q divided by A is equal to sigma, where sigma is called surface charge density. Sigma is called surface charge density is equal to Q divided by A. At the end we got electric field E is equal to sigma divided by 2 epsilon naught. It is the expression for electric field. Depending on sigma, if sigma is positive, we say the charge on the surface is positive, automatically electric field is acting outward. If sigma is negative, charge on a surface is negative, automatically electric field is acting inward. This equation clearly gives idea that electric field is directly proportional to surface charge density. If surface charge density is more depending on a strength of the charge on the surface, automatically electric field is also more. And this is also one of the important derivation mainly for 3 or 5 marks in annual exam. At the end, for a thin metal sheet, we got electric field E is equal to sigma divided by 2 epsilon naught.